Okay, so welcome back. So last time, and actually for the next, I'd say it won't be probably until the end of lecture on Friday that we'll get out of Egyptian math. So concurrently, as I mentioned last time, there was this development in Egypt and in Mesopotamia. It was pretty much contemporary, and you're gonna see an example of the things that. So I mean, by the end of lecture today, we'll talk about basically how the Egyptians used. They essentially used base 10, like we did for So their number system wasn't quite exactly like ours, so they didn't have place value as you saw with the table that I showed you last time, but it was still a base 10 system. Um, but basically, the Egyptians. So, well, I would say that we probably less carried over from the Egyptians than. Well, I don't know that that's true either. So the Egyptians, their influence on early Greek mathematics was big, whereas the Greeks didn't get a whole lot from the from Babylonian mathematics, but um, uh, you'll see the difference kind of in the problems that they considered, and there's a curious I won't spoil the fun, but there's a curious thing that we borrowed from the Babylonians that's still used today. Uh, uh, this has to do with the root of why we count, for instance, time as base 60 has to do with the Babylonians. So anyway, I wanted to give a couple more examples of how the Egyptians might use this method of doubling, or this funny method of multiplying without reference to this kind of standard algorithm that we are used to. That very much relies, of course, on our number system. So okay, let's try to apply the same doubling system for division. And I put doubling in parentheses there because while they typically were using powers of 2 here, it wasn't something that they always did. And I'll do an example here in a second that shows um, another thing that they did, actually coming directly from the Rhiine Papyrus itself. So let's do. So let's suppose we wish to divide, say 184 by 17. So how can we do division using the doubling method? So the idea here, as before when you were doing multiplication, is we start with one of these things. So we're going to start with 17, the thing that we're dividing by. Okay, so we're going to start with 17, and we're going to track the multiples of 17 here. So we're going to double this, so 17, if we double that, that's 34. If we double that, that's 68. If we double that, that's 136. And we can stop here because 136 is going to be the largest multiple of 17 that is less than, or, well, I shouldn't say multiple of 17. It's the largest power of 2 times 17 that is less than 184. Right? So there are multiples of 17 that are less than 184, but not as a power of 2, right? If I double this, I get something bigger than 184. So I stop here, okay? And then what I do is when I stop at this last row, I check that off, right? Because if I subtract this from 184, right, I'm guaranteed to be left with the smallest amount from this process. So then I would subtract, I would do 184 minus 136. And when I do that, I get 48. Okay. Now, once I get 48 here, I look at the same list, and I would pick the largest multiple of 17 that is less than 48. So that's 34. And I check that. Okay. Now, what do I do? So now the idea is to do the exact same thing. So I want to, here I began with 184 that I was dividing by 17. I subtracted 136 from it to get 48. I look at the table, largest multiple of 17 that is less than 48 is 34. And I subtract 34 from 48. So 48 minus 34 is 14. Okay. And 14 is less than 17. And so this is the part where the Egyptians would have said, oh, this means that our process terminates. Our process is over now. And the reason for that is you have now gotten to a point where when you subtract this entry in the list from the resulting thing from the previous step, you get something that is smaller than the thing you're dividing by. Okay, so there's nothing to do from here. And this tells you that you're done. So what do you do to get your answer? You add the entries in the checked rows. So here and here. I have 8 plus 2. 8 plus 2 is 10. And I'm done. What do I mean that I'm done? What is the actual answer? From this process, the Egyptians would say, well, then my quotient is 10, and there's a remainder of 14, sorry. So the answer is this quotient is 10 with remainder 14. And of course, you can check that that is indeed exactly what you get here. Okay. Now think for a second why that works and how you could reproduce this. Okay. I mean, in fact, if you were to write this out, right, all this is saying then is that 184 is 10 times 17 plus 14. And it certainly is that, but of course, dividing by 17, is there anything smaller here? Or sorry, is there any other way of rewriting this, in such a way that you have something times 17 plus something where this r, right? If you've seen this written, right, this is so this is say n is equal to q times p plus r, where r is strictly less than q, but it is bigger than or equal to 0. Right, so a remainder could be 0, but a remainder definitely needs to be strictly less than q, because if it were bigger than that, then I could redo this, right? I could regroup what is written here, right? If 14 was bigger than 17, then there could be a regrouping here that would result in this r being reduced, right? And that's not what I want. So I want my r must be strictly between, sorry, not q, but p. If I've written it like this, such that q is 10 here. then R needs to be strictly less than P. Okay. Okay. All right. And yeah, whenever, in general, whenever I'm writing off the page, just let me know and I'll move it. I'll move it up. Okay. So, this process for multiplying could be used essentially, uh, in this inverse way of you could actually use it to divide similarly. Now, the question is, can this doubling process always be used for any numbers we pick? The answer is yes. And the Egyptians likely knew this, although, as I mentioned last time, they wouldn't have, or they didn't prove this, and they probably wouldn't have been able to prove this. But they had done enough of these that they knew that this was okay. So the big question is, can you use this doubling for any integers? That is, for any multiplication or division problems that are either, A times B or A over B. So can I use it, where A and B? Say positive integers, it doesn't really matter here. So can we use this doubling method always? So the answer is yes. As we'll see, this is equivalent to saying that every number has a base 2 expansion. So every such number has a base 2 expansion. Okay. Okay. All right. We'll see exactly what that means here in a second, but the point is that you can express any of these numbers as this base 2 expansion, meaning a sum of powers of coefficients times powers of 2. Okay. Remember that, of course, 1 power of 2 is, so remember that two to the 0 is 1, and that's a power of 2. Okay. So if you're, for instance, I think last time we did a multiplication problem involving 17, right? So something like 17, right, is 2 to the 4 plus 2 to the 0, right? 16 plus 1. Okay. But of course, you might say, well, 16 is really close, or 17 is really close to 16, so it's really close to a power of 2 already, so that's more obvious. But you can do this, you can pick whatever you like here to figure out what's going on. So you can just try this actually. Here's something for you to do. So try write, say, do something like 357. Write 357 as a sum of powers of 2. Okay. Okay, and you can do this, as I said, for any number. So this Egyptian doubling method would always work. Now, the problem is that this wouldn't always be the most efficient way to go about it, of course. And the Egyptians recognize this as well. As I said, they actually understood, or they actually used a base 10 system. And of course, in a base 10 system, multiplication by 10 is easy. So whatever base you use, as we'll see, when you multiply by the base, it's easy. You're shifting digits, basically, which is why in our system, which is base 10, multiplication by 10 is easy. To show you an example of shortcuts that the Egyptians used, here's so the Egyptians recognized that sometimes it was quicker to also include in this algorithm multiplication by 10. So here's an example. This example actually comes directly from the Rhiine Papyrus. This is problem 69. So this is problem 69 in the Rhiine Papyrus. So this problem asks to calculate the number of row of flour in each loaf if 1,120 row of flour is made into 80 loaves. So this is compute the number of row of flour in each loaf if 1,120 row of flour is made into 80 loaves. Okay. So what we're being asked to do, obviously, is to divide 1,120 by 80. Okay, and so doing like we did before, we begin by tracking multiples of 80. Okay, but 1,120 is a big number. So the Egyptians would have said, all right, we could double 80 a bunch, and we're still going to do that, but it would be quicker if we actually recognized that I could multiply 80 by 10. That's an easy thing to do. So I would get 800, and that's 80 multiplied by 10. And if I were to subtract 800 from 1,120, I'd be left with 320. But 320 is going to be one of these doubling things that I get from doubling 80 twice. So to see that, 80 doubled once is 160, and doubled again is 320. And so if I check that 800 and 320 sum to 1120, my answer is 14 loaves, right? So my answer is 10 plus 4, or 14 loaves. Okay. And so it wasn't just doubling that was used in these things. You could use multiplication by 10, for instance, as a shortcut here. And again, multiplication by 10 was nice for the Egyptians because they used a base 10 system. Okay. All right. So it wasn't just these simple arithmetic of multiplication and division that the Egyptians were proficient at and had figured out methods to efficiently do. There's a few other things. So they could extract square roots, right? Which, if you don't think about it too much, you might not find some of the extraction of square roots that impressive. But remember, right, there's very little computationally at their disposal. So being able to, uh, oh, did I say, what did I say? 14. Oh, we're made into 80 loaves. That's right. That's right. Yeah, yeah, yeah. So not 14 loaves. So 14 row per loaf. Yes, that's right. Thank you for that. So the extraction of square roots, right, is a nastier thing than you might at first think, because right, there's no calculators, uh, no ability, no slide rule, no anything like that. This was purely, by hand extraction or approximation of square roots. So, what were the things? So the Egyptians knew how to extract square roots. Um, as well as how to solve linear equations. Yeah, so ax plus b equals 0, as we would write in modern language. They could solve these things. Um, so in fact, they used the hieroglyph H in the same way that we use X. For an unknown quantity. Okay. Now I should be careful here because, and this is always a danger. I wrote the linear equation they're solving like this, and when you look at this and you immediately try to solve it, you begin manipulating this equation, right? This notion of balancing. So that was not always exactly what ancient mathematicians did. In fact, the notion of doing those sorts of operations, it was a lot more subtle than that. They didn't necessarily do something like that. Their methods for solving things, were equivalent, but there's a distinction to be made between the doing of some basic algebra in this way and kind of the methods that they use. So I'll get more into that later, but they could still solve equivalent expressions like this. What else? What else are things that they could do? So they used the formula 4/3 to the fourth times r squared for the area of a circle. Right? So this was their formula for the area of a circle. Of course, the actual area is pi r squared. So since the area of a circle is pi r squared, this implies an approximation. So our approximate value of pi to be approximately 4/3 to the fourth is like 3.16. Okay, so not too bad. All right. Okay. So it's kind of a neat fact. Now, I should say that one of the most interesting things about studying the history of math is to see which concepts certain civilizations got hung up on. So all of these, every single one of these civilizations got hung up on something that we would find kind of ridiculous. We would say like, why were they so bothered by this? And without exception, this is true of every single civilization that did, every single ancient civilization that did math had some thing that they really, really struggled with that we would find, strange that they would get so hung up. So, for instance, when we get to the Greeks, we will see that they were very, very bothered by, they were very, very bothered about doing algebra with quantities that weren't rational. So rational means that, they can be written as a ratio of two integers. And so the Greeks were terrified of doing computations with things like square root of 2 or square root of 3 over 2, quantities that involve these irrational numbers. And so they didn't really treat them like numbers, because they, in a way, they almost didn't believe that they were real numbers. They were just kind of these terrible things that had to be dealt with. But in order to get around dealing with them like numbers, they had to come up with this. It was called the theory of proportions, and it's actually the subject of an entire book of Euclid's Elements, was in dealing just with essentially fractions. Of course, like there was no problem in just treating them like fractions like we do, right? If you're going to do arithmetic involving irrational numbers, it doesn't bother you at all, right? You don't care that whether the numbers are rational or irrational. The actual arithmetic involving the numbers doesn't care. But the Greeks were really, really bothered by this, so they came up with this very complicated theory of proportions to deal with this, which is actually really interesting. I'll try to get into that a little bit when we talk about the Greeks again. But anyway, every single ancient civilization that did math had some concept that really tripped them up. So for the Egyptians, they had a very interesting way of dealing with fractions. So the Egyptians had an interesting, should say, tradition of dealing with fractions. So what they did is they insisted on writing every fraction, except there was one exception, I believe 2/3, except 2/3. So for some reason 2/3 is exempted. Okay, so except 2/3. They wanted to write every fraction as a sum of unit fractions. What's a unit fraction? A unit fraction is a fraction that is 1 over n for some n. Okay. So what do I mean here? Right? So this is an important distinction in Egyptian mathematics, because it turns out this is a very tricky thing, and it's not at all obvious. I mean, there are a ton of problems that you can come up with for expressing certain fractions in this way, and it's just not at all clear how you would necessarily do that, or whether or not you can even do this. In fact, I'll give an example of a problem. I think it's still an open problem involving this, that it's just not clear from the statement itself that this is something that's so hard to do. And so let's do some examples. So some examples here, like 2/9, right? So how would Egyptians write 2/9? So they would write 2/9 as 1/6 plus 1/18. Okay. So you can check really quickly that this actually works, right? So if I put these in common terms at 18, this would be 3/18, and this would be 1/18. So the sum would be 2/18, which is, or sorry, 4/18, which is 2/9, right? Okay. All right. What about another one? So what about say 19/8? How would they write 19/8? So they would write this as, so first of all, this is an improper fraction, so there's a whole number involved here. So this would be 2, which is fine, plus 1/4, plus 1/8, right? Because 18 goes in, or 8 goes in 19 twice, and what is left over there is 3/8, and 3/8 is easy enough to write as unit fraction. Okay. Okay. So even though they typically were fine writing 2/3 as just 2/3, sometimes they also wrote 2/3 as a sum of unit fractions. So this, of course, can be written as 1/2 plus 1/6. Okay. All right. So then, why does this matter, right? Other than just being annoying and taking a while, to write this out, why does this matter? So the Egyptians had a difficult time dividing with fractions. Had a difficulty in particular with dividing and multiplying fractions because of this. So say you wanted to divide the fraction 5/13 by 12. All right, so suppose I want to divide, say, 5/13 by 12. Okay, so for us this is no problem. We can just immediately say, oh, 5/13 divided by 12, that's just 5 over 13 times 12, right? So this is 5 over 13 times 12. We don't even care what 13 times 12 is. It's just, we can just slap it as product. So once we see that, right, dividing a fraction by any whole number like this is no problem at all, right? Because our scribes have worked out multiplication tables for us, and so it's not even an issue. Okay, but how would this work for Egyptians? Since Egyptians insist on writing 5/13 as a sum of unit fractions, how would this go? So this is actually, so basically, in order to do this, Egyptians wrote these tables. So they wrote tables listing unit fraction decompositions. For fractions of the form 2 over n. Okay. So in fact, one of these tables is directly in the Rhind Papyrus. So here n is an odd positive integer. Okay, so one of these tables is in the Rhind Papyrus. So one such table is in the Rhiine Papyrus. And to see how you would do this problem of dividing 5/13 by 12, let's consider the following. So note this table gives 2/13 as the following decomposition. So 2/13 is 1/8 plus 1 over 52 plus 1 over 104. Okay. I want to use this together with the fact that 5 is 2 times 2 plus 1. Okay. So 5 is 2 times 2 plus 1, which means that I can multiply this by 2 and then add 1 over 13 here. So if I want to find 5/13, I can split this essentially, right? So that's exactly what I'm going to do. Okay, so maybe I'll actually leave that decomposition right here. So table in the Rhiine Papyrus gives that decomposition. So then 5/13, that's the same as 2 times 2 plus 1 over 13, which I can write as 2 times 2/13 plus 1 over 13. But 2/13 has this composition here. So this decomposition coming from this table gives me 2 times 1/8 plus 1/52 plus 1 over 104 plus 1 over 13. Okay. So then multiplying so multiplying through by this 2 and then simplifying these fractions, I would get 1/4 plus 1 over 26 plus 1 over 52 plus 1 over 13. And so, as desired, I've written 5/13 as a sum of unit fractions. Okay, and then if I wanted to do 5/13 divided by 12, right? How would I do that? Well, now it's easier. So 5/13 divided by 12 would be this expression divided. Each term in the sum is going to be divided by 12. So this would be 1 over 48 plus 1 over, so dividing by 12, 12 times 26, that's 312, plus 12 times 52 is 624, so this is 1 over 624, plus 12 times 13 is 156, so it's 1 over 156. Okay, and this is how the Egyptians would have handled dividing the fraction 5/13 by 12. Okay. All right. So, this is, so someone asked here, so Graham asked, is there any particular reason they didn't just write 2/13 as 1/13 plus 1/13? So it wasn't just that they wrote it as a sum of, because that's right, that brings up an excellent point that, of course, you could have just written, like any fraction you come up with, you could have written this as, 5/13, right? 5/13 could have just been written as 1/13 plus 1/13 5 times, right? They insisted that there be distinct. They insisted that the denominators be distinct. So maybe I should say that. So I'll make an extra note here. Egyptians insisted that these unit fractions be distinct. That's the reason why. Sorry if I don't know if I said that when I first stated it or not, but they actually insisted that yeah, these things be distinct. So it wasn't enough to just list each of these fractions as, you know, just a copy of the same unit fraction. No, they wanted it specifically. They wanted all these fractions to be distinct. Did the Egyptians start out with the improper fraction and break it down, or did they only use 1 over n summation form and never recognize the ability to turn the sum into a single term? No, they actually, so they would start with say a fraction, right? Well, so they would start with a division problem. So say 5 divided by 13. And they understood that, okay, that's not, because 13 is not, 5 is not divisible by 13, that is going to yield a fraction rather than a whole number. So they understood that, and they then wanted to, once they had that, they were like, okay, the fraction that it's allowed to be, basically, like 5/13 is a fraction, like they didn't write that. For them, a fraction was only one of these sums of unit fractions. Okay. So it's not like they started with the improper fraction and then broke it down. They would start with in the context where they were doing, they had the number represented by a division, so 5 divided by 13 or 18 divided by, 7. And rather than like writing that as a fraction and just going with it, right? Because we know that you can write those for any of these fractions we started with. Like, there's no need for any of this. You can just deal directly with this fraction. They didn't do that because to them, this wasn't a valid expression. So this is fine, but 5/13 is no good. And I'm not entirely sure why this is. How would they apply this to their needs? Well, so I'm not sure why they insisted on the unit fractions. I'm not entirely sure, what they thought they were getting out of this, and I'm not sure that there was much of a benefit. It could have been just something that was developed. Buying a certain amount of grain would be easier to weigh out by standard weights. It's possible. That's possible. Yeah, how are they able to divide unit fractions by numbers but not fractions like 5/13? Well, the way that went was, imagine that you are told, right, that the only thing that is properly called a fraction and properly counts as a number, basically, is something that looks like this. And you're, dividing this by whatever number you want to. Dividing this again by 5 is no problem, because dividing all these fractions by 5 works in exactly the way you know it does, because there's this 1 here. Now, of course, we know that it doesn't matter that there's a 1 there. That 1 could be whatever, and this fraction division would work in the same way. But for Egyptians, they had set up this system where they thought that these were the only valid fractions, basically. Okay. And so it's not entirely clear, and I can find out for you. I can look more. It's not entirely clear why they were so caught up on this, but this is one of those things. We're going to see this over and over again as we progress through these civilizations, that all of them had some interesting worries, some things that they were very concerned about that we know now just doesn't matter. And it seems funny, that they would be so worried about it when they clearly had the tools to deal with these fractions in the way we do. But for whatever reason, 5/13, that's a scary thing, but expressing it like this is perfectly fine. So let me point out, there's a couple of interesting related things. So the question is, can you always do this? right? So can you always express these types of fractions as sums of some particular types of unit fractions? So in fact, so 2 over 2m plus 1. So 2 over odd number can always be expressed. So this can always be expressed as a sum of the unit fractions 1 over m plus 1 and 1 over m plus 1 times 2m plus 1. Okay. The Egyptians, however, didn't actually probably know this recipe because they didn't follow it. So Egyptians didn't always follow this. So the Egyptians didn't always follow this, however. So in fact, Ahmose, the writer of the Rhiine Papyrus, wrote that 2 over 45 was 1 over 30 plus 1 over 90, which does not follow that recipe. Okay. All right. So here is a question. Okay. If n is an odd integer greater than 4, can 4 over n be written as a sum of 3 distinct unit fractions? So this was open. So this is an open problem. It was open as of like 20 years ago, so I'm not sure if it's still open. So this is an open, I'll put open star because I'm not sure if someone has solved this in the last 20 years, but this is an open problem. Okay, this is actually stated first by Paul Erdős. Okay. So the reason for me stating this is to show that even very simple questions about these unit fractions can be really tricky and very hard to get at. Now, the question of whether or not you always have some unit fraction decomposition, that can be answered a little bit better with what comes next. So we'll talk about other bases for a number system next. Because that's going to tie together both Egyptian mathematics and what comes immediately after, which I'm going to talk about Babylonian and Mesopotamian mathematics, which is happening in the same time frame. Okay, so within plus or minus 100 years, what's going on in Egypt is and what's going on in Mesopotamia is exactly what we're going to talk about. So these were contemporaries doing this. Now, there's a direct line between modern math and Egyptian math directly through the Greeks, really. Mesopotamian math is pretty impressive in its own right, though the way that it was discovered was kind of separate, and it's hard to say how much of Mesopotamian math kind of filtered through to the Greeks, but it's certainly possible that there's a lot of things they owe to the Greeks. For instance, the Pythagorean theorem was most likely first used by Babylonians. So anyway, we're out of time now, but that's what we'll discuss we'll discuss next time. So next time we'll do scales of notation, that is different bases of number system. As I mentioned at the beginning of class, so the syllabus page has been updated, so have a look at that if you haven't already, and maybe I'll mention that in the first couple minutes of class. Next time I'll kind of go over that. Okay, so I will see you all on Friday. No homework of any kind until next week. Maybe on Monday I'll post a small homework assignment. So anyway, that's that, and I'll see you all on Friday. Hi, Alvion. I saw your question. Do we stop because 17 isn't less than 14? That's right. So in that previous, let me see if I still have the sheet that you're referring to here. So here, right, in this process, the thing that tells us to stop is exactly, that we got to a thing that is smaller than the thing we're dividing by. Yeah, that's what tells us to stop. So try this with, try doing this. Do the division 355 divided by, 355 divided by like 19. All right, try this. Try this problem using the same method. Okay. So that's something you can try to nail down what's going on there. Okay, all right, I'll see you all later.